Thanks. So this statement is always true. I may or may not. That's fine. So first correction, people say I'm from Linz. Every Austrian who speaks to me knows that's clearly not true. I'm German, and I'm happy to be from Jena. I'm not from Linz, also a nice city, but doesn't matter here. Okay, so what I'm going to talk here is some kind of very basic or philosophical type of mathematics. You will see. I hope you find it interesting, and we can at the end discuss a little bit about that. A little bit to the story. I'm doing mathematics for longer than I'm usually willing to say, but sometimes in mathematics, it's you ask the right question and you are hooked. And this is one of the things. I'm doing mathematics now for a while. I did write some things I think are interesting and so on. This is something I was working on for a year, and it was really fascinating. So please, yeah, maybe you will see. Maybe you will understand it. So the problem is extremely basic. It's really we all want to approximate functions or ground states or whatever operators. We are doing very crazy stuff, right? But now assume we step back a little bit. We go back to mathematics from the hundreds of years ago, and we just ask. We just want to recover a vector. We just have a bunch of numbers. We have m numbers, and the goal is recover them by having a smaller number of measurements. So the idea is probably just to have a picture in mind. What I mean by an algorithm in general is you have some class of inputs. Because we only can do measurements, we only can work with finite amount of numbers, with a finite amount of data on a computer. You have some element here, which is now this x guy. You map that to a vector where you have n numbers. I call them lambda 1 of x up to lambda n of x. But that's just an n dimension, a vector of n and maybe complex numbers, I don't care. So, right, like this. Now you want to come back. Yeah, that's only this picture. There will be no details here. Yeah, and then you go back to some approximation of x. Whatever this means, right? Yeah, we'll do it precisely in a second. For vectors, there is nothing really special. That's what I understood in general of an algorithm, what a computer can do. You make some measurements here. You measure. E missing, I don't know. You measure and you recover. Okay? Clearly, and I get that, you should pose restrictions on the recovery map and on the measurements. It's clear, otherwise it makes no sense, right? From my point of view, I don't care if a computer can do it for a second. Judge yourself if a computer can do what I present to you. I'm working with the theoretical concept. And measure a mapping to Rn from some general thing. In this case, in the beginning here, I'm just talking about Rm, and m is very, very big. At least much, much bigger than n. And now, okay, so you produce n numbers, and now you go back to an approximation. Okay, so we want to recover an arbitrary vector. Clearly, since things cannot be done exactly in this case, or not clear, but it cannot be done exactly, we have to specify some error that we want to do. Think of machine precision if you want to, in some norm, right? So you have a vector in Rm, and now you need to, for the approximation, you need an error criterion. Please stay there. It's really the only thing I'm doing. So it's like you want to find that this is small, right? This. Okay. And the general theme is you only know nothing about x. Nothing. It's only a bunch of numbers. I have it in my head, and you are allowed to ask questions to me. Okay? Just ask. I have 20 numbers. You can ask 5 questions. Do you think you can find my 20 numbers? We will see. Okay, so you know nothing about x. You can only compute a certain measurements and pieces of them that you can choose. How many measurements do you need? And I very much hope, and I think most of you already have an intuition and an idea, and this intuition and idea is mostly correct, and I will give you a proof about that. No, at this point I only mean what you think about measurements, anything is fine. Okay? So now assume these measurements are linear. It's the very typical thing in approximation theory, numerical analysis. Function evaluations of functions are linear. Fourier coefficients are linear measurements, and so on, right? So everything, most things that you imagine as linear measurements And that's why most people think that's the end of the story. Okay? So less than m linear measurements are useless, completely useless. Let me give you a proof. Assume you fix your n measurements, right? Then this n here can be actually represented as a matrix. So, and if n is smaller than m, and those are linear functionals, then we know that if I get some information y out of my measurement matrix, there's a whole affine subspace of Rm with dimension larger than m minus n that get the same information. Okay? So you have an infinitely large, you have a whole affine subspace, and all guys on the subspace have the same information. And since all of them have the same information, you cannot distinguish them. So every reconstruction, because your computer only knows the data, so every reconstruction phi that you can think of, no matter how clever you are, they may be arbitrarily far away from the true value of x, just because they are indistinguishable. Okay, fine. Now we realize, okay, linear is bad, right? And why didn't I pose any restriction on x? I could say, yeah, x is in the unit ball or whatever. I could do that. Didn't change the story much, by the way. Okay, continuous information is maybe more interesting, right? Assume I can evaluate certain functionals that are not linear but continuous. I can solve certain optimization problems related to my input or whatever, right? So the thing is, the same is true. So, and that follows from a general and important result, I would say. It's the Borsuk-Ulam theorem. It says that assume you have an arbitrary continuous mapping from Rm to Rn, and n is smaller than m, then for every r, there are 2 points at distance 2r such that the information is the same. This is sometimes called the Harry-Ball theorem and stuff. So there are many reformulations which just say on a sphere, a continuous function on a sphere has 2 antipodal points. That's more or less the essence here. But again, the same statement. That is, you cannot distinguish between these 2 vectors, no matter how you fix your information mapping. And so every approximation, so these 2 guys are at distance 2r from each other, and r is arbitrary, so I can make r bigger and bigger. So again, you cannot distinguish. There is no provable error bound. Story told. That's done, right? So again, less than m continuous measurements are useless. Okay? But now we come to real numerics, kind of. That's the type of... now things get more difficult to study, but for me more interesting. That's more or less my field of research. So why should I fix the measurement mappings in advance? Well, what is the reason for that, right? If I want to compress or if I want to approximate and my algorithm is running, then inside of my algorithm, there will be a for loop and there will be an if requirement and stuff like that. So everything in a typical computer program is adaptive. Why not? It's fine, okay? So it's probably better to use the already obtained information, so the first k minus 1, and then choose the kth functional based on them, right? And this is what I call adaptive measurements. Right? So think of computing some function values, you know where the function is big and small, and now I'm putting my next point somewhere where it's big. Right? So the very prototype of an adaptive algorithm is bisection. Or is the bisection method actually. Many search algorithms are adaptive and stuff. Okay, so we call this adaptive. And to be precise, the choice of the kth functional really clearly depends on x here, but the choice depends on the outcome of the first k, but also on what they really are as a functional. Just for those who know the details, there, if you forget about this here, then you are more in the field of statistics than in the field of optimal recovery. Okay, why should I fix that in advance? Unfortunately, the fact remains that less than m linear measurements are useless, even if we choose them adaptively. You cannot do anything. I have m numbers, these m numbers are unrelated. It doesn't matter how I choose the things, right? You must think of all elements of x are maybe just in a ball, not in an ellipse, just in a ball, and no matter how many slices I put there, the outcome is still a ball. It's a lower dimensional ball, but it's a ball. We want to prove it, we prove it. As before, assume you start with some x, You apply your adaptive measurements. These adaptive measurements, you end up with some y, and you end up with some functionals here, because this is how the procedure works. And again, since you know now these lambda y, there is again a whole affine subspace with this. So which means, no matter which v I'm starting with, I would have chosen the same functionals. The method is just doing the same for every element on the subspace. So with the same argument than before, you cannot distinguish them. So again, the error might be infinite. Okay, maybe you already know where I'm heading, right? So, but what happens if I consider both together? I allow adaptively chosen continuous measurements. Do you think you can do something better then? Is it reasonable to believe that you can save 1 or 2 or 5 measurements? Maybe you only need half of them. Okay, also no, nothing to see here. Thanks for your attention. No, clearly it is possible to do something. The quite surprising answer here is yes, and it's a brutal yes. So this is the result. You actually only need logarithmically many measurements then. Okay? Let me read it out for a second. And I will come to a short example in a second to see how brutal this is. So we were not expecting this. So we fix m and epsilon. There is an algorithm, and I will explain this algorithm completely to you. It's easy to, if you want to, you know it. It's kind of easy. But we didn't know it before. So there is an algorithm that uses at most log m plus 1 adaptive 1 Lipschitz continuous measurements and satisfies this bound here for all x in Rm without any restriction on x, without any structural assumption, whatever, right? So this here directly implies that the algorithm is kind of stable, right? So because it has a small error for all x, that's just triangle inequality to get that you have something like this. So this algorithm is even kind of stable. But it depends on your definition of stability of an algorithm. Usually stability includes kind of continuity, and this algorithm cannot be continuous. So repeat that again. There cannot be a continuous, completely continuous algorithm because Borsuk-Ulam theorem forbids it. So this algorithm here makes jumps somewhere, right? But very, very tiny jumps. Okay, so maybe let's say it again. Assume you have 10,000 numbers, right? If you do it linear, continuous non-adaptive, or linear adaptive, you need 10,000 measurements. Done. If you do it with Lipschitz continuous measurements, and you will see that those are kind of realizable by neural networks, just to use this fancy word also in my talk. So if you do it like this, then for 10,000 numbers, you can do it with 8 questions. Well, if I have 10,000 numbers in my head, 8 questions are enough for you to get them, just to get it. Please. Sorry, yeah? Exactly, yes. It does not depend on epsilon, and to be honest, what we are doing here is close to topology and dimension theory to some extent, because it's really about representation, exact representation of vectors. Yeah, so yeah, the number of measurements does not depend on epsilon. If this is magic, but the same was true with linear measurements, right? Because for linear measurements, you can do m. You m minus 1 are not enough, and if you have m, then m. There is no epsilon there, because you can do it exactly, actually. You need log m measurements. What do you mean? Yeah? Dimension 2, yes, of course. You can just take the coordinates. Even linear measurements are fine there. This result is trivial for m smaller than 4. This result is trivial. No problem. Okay, so this does not depend on epsilon here. I found this impressive. And if I have time, then at the very end, I can tell you the beginning of the story, a little bit of history. Most likely, I won't have time for this. But the point is, we were actually trying to prove the opposite, because we thought continuous measurements together with adaptation, that cannot help much, right? Why should it? I don't know. It was just our feeling. And we were working for 9 months or so until we thought, let's try the opposite. And then it was rather fast. That's, as I said, sometimes it's about asking the right questions. Let me explain the algorithm. I hope you are already a bit curious about that. The algorithm is based on a specific type of coloring of the whole RM, of the whole space. Okay? So we take a partition of Rm into these sets, di, I will make a picture in a second, in these sets, and a coloring map. So these sets here, this partition is colored. And it must be colored in a way that each of these sets has a small diameter, and the coloring here, this T of I, is just the color of the ith set here, right? And if two sets have the same color, then they must be strictly separated. Okay? So here, diameter and distance are with respect to the given norm. Everything here is also independent of the norm. If you do L2 norm or infinity norm, I don't, right? It's the same on this level. So these are two colorings in dimension 2. These are two colorings in dimension 2, right? So you see you need 3 colors, as I said, m plus 1 colors, and they are clearly separated here, right? If you have 2 with the same color, that's fine. If someone of you loves to play around with paintings or so, if you find a generalization of this very, very nice tiling here to a higher dimension, I would be very interested. We tried hard and we asked some expert in the field, and we really don't know if this is possible. 1 minute. But this one here is rather easy to generalize to high dimensions, and it's somehow related to the sparsity of the vector. Yeah. Yeah? Not touching the distance here. And maybe that's. Yeah, that's about general maps. Every map can be colored this way, but as you see, there are better maps. Yeah. And by the way, even if you find some map, you will see later how we use the coloring. If you have an idea how to implement this on a computer, and you don't need m plus 1 colors, but you need m squared colors, I don't care at all. It would be amazing to see, right? If you have an easy, it's all about having more colors is not a problem, because this m only comes in logarithmically later. Yes, but less than m plus 1 color does not work for any mapping that's related to the so-called Nagata dimension. And the Nagata dimension is, in RM, all these dimension things are the same. But if you think of coloring on general manifolds or other topological objects, then the Nagata dimension is exactly what we are doing here. Okay, so this m plus 1 is Nagata dimension plus 1 if you do everything here not on RM but on more general sets, if you want to. Sphere or so, there you can save 1 color and stuff. It's not really represented. Okay, this was the coloring. What's the first stage? To find an epsilon approximation of a vector, it is clearly enough to find the set where it's in, right? So you take a coloring, you scale everything down, because you can scale the coloring, why not? So you scale it down such that the diameter here is smaller than epsilon. Maybe I should change it here for next time. Yeah, whatever. I make the scaling here because it was easier to prove or so. But think of, you take the coloring, you scale it down such that each of the sets has a diameter epsilon. And so then it's enough to really find the set where it's in, right? If I know my x is in the set and the set has diameter epsilon, I can output any element of the set and I'm done. Okay, so the question is, how can I find the set? And it's like this. We first find the color. We first want to find the color of x. So for this, we define these IR, the correct indices, and ER are all points with color I, with color R here. And now what are the continuous measurements then? The continuous measurements are just, for a subset J, I just compute the distance to the union of these sets. Okay. Yeah, I understand computing the distance is complicated, maybe not possible on a computer, but again, I'm talking about kind of philosophy, right? It's clearly Lipschitz continuous. And for our purposes, that's more than enough. Okay. So, and once you can compute these functionals, then, so this functional tells you if x has any of the colors in J, so we can just use log m plus 1, forget about the plus 1 in the main result is changed by a trick later. I did not want to write something wrong here. Okay. So we use about log m measurements of this form and bisection method to find the correct color of x. So we can output, after log m steps, we can say, okay, x has this and that color. But if we have the color, there are still a lot of them, right? Actually, there are infinitely many of these things that have the same color, right? So what is the second stage? The second stage is find the correct box. And this can be done with any continuous functional such that the images of these sets here are disjoint. Don't think too much about details. This is an example. Okay? If I'm allowed to evaluate this functional, which is again Lipschitz continuous, which Lipschitz constant 1, if I'm allowed to evaluate this, then the correct index I, where x is in, is given by this formula. Okay? So now I have the correct box, and the output of my algorithm can be any element from this set. And I'm done. Okay, did we really construct a clever algorithm? I'm not so sure. I have no idea, right? But this is not we did not invent the whole setting. The setting of using continuous measurements as a benchmark and using arbitrary reconstruction methods is not done by us. It's done by other people in approximation theory, and there's a little bit of a fight from time to time where they say their setting is better and we say our setting is better, and you know how it works, right? And so at some point we decided, so let's look what they can really do. And what they can do is amazing, but for us it more shows that continuous measurements are just an unrealistic thing. It's just something, Lipschitz continuous measurement are unrealistic. Otherwise, you must believe what I just presented to you, and this means what you just have seen is the most impressive compression method on Earth. I don't believe it, so I actually think that my assumptions are kind of weird. But what are our assumptions? We only have two of them. The first assumption is, if you have a Lipschitz mapping, then we can compute values of it. So all Lipschitz functionals are admissible as measurements. That's assumption 1. And assumption 2 is, information can be chosen adaptively. So the second one is really widespread. In numerical analysis, every algorithm uses it. So we really don't see a problem with the adaptivity, which means the only assumption that could be too unrealistic is the use of arbitrary Lipschitz measurements. Okay. 5 minutes or so? I think I'll manage. So let me do a little bit of real march, just to see, maybe it connects more to what you have done. Maybe you're not interested in approximating vectors or so. Maybe you have more general objects, functions, operators, whatever. So assume now you have a set capital F, subset of any metric space, and you want to approximate elements of this set in the norm of Y. I'm just repeating everything in a more general situation, by the way. So we allow algorithms of this form, so we compute n measurements that can be chosen adaptively, and then we take an arbitrary reconstruction map. And what we are asking for, because I'm doing more complexity theory than real algorithm stuff, is what is the minimal worst case error in this setting? What does it mean? I take an algorithm, I compute the distance of the output of the algorithm with the real element, that's the distance here. I take the worst case error by taking the supremum over all elements of F, usually a unit ball or something like this, and then I'm taking the infimum over all algorithms of this form. And this guy is called the minimal worst case error of algorithms that use at most n continuous adaptively chosen measurements. Right? That's the object. It's totally fine. And we want to see if adaptation is the powerful thing. Is it the choice of measurements? Maybe. But is it only the adaptivity? And in this case, it is. So if we want to compare this guy here now with the error of algorithms using only non-adaptive measurements, so that's given like this, right? So n is just a continuous mapping from F to Rn, and phi goes from Rn to Y, right? So here is no adaptivity allowed. And this is the thing. And one of the theorems we have, I only present the Hilbert space setting because the other thing is a little bit complicated. We need strictly convex norms and things and constants related to this. But in a Hilbert space setting, everything is easy. So let F be the unit ball of a Hilbert space, Y is also a Hilbert space. Then we have that with adaptive with adaptive algorithms that use n information, I get the same like an exponential large number of non-adaptive measurements. So I really get some kind of an exponential speed up just by allowing adaptivity. And by the way, that's the same for the bisection method in many situations, right? The bisection method, just for finding the zero of a function, right? You have clearly an exponential speed up by using adaptive choice of function values, right? And we know to some extent prove that a similar thing happens in this much more general situation here. And by the way, the case of Hilbert spaces is special because these numbers here, the non-adaptive errors, they are equal. There is some deep theory on operators, Peach and guys with S numbers and so on. So these numbers here are really the same, like Kolmogorov numbers, Gelfand numbers. And for you, that I edited a minute ago, this guy here are just the eigenvalues of the embedding, right? So these are just the eigenvalues of the embedding from F to Y here, the 2 to the nth one. So if you know the eigenvalues of your embedding guy, then you can see, also in this setting, it's an exponential speed up. Minutes, it's fine. So some final remarks. If this Y is an LP space, so if we want to make, from the very beginning, if you make this approximation here in an LP norm with P equal to 1 or P equal infinity, then everything I did here was piecewise linear, right? So all these functionals are piecewise linear, and since they are all piecewise linear, they are, and one Lipschitz, I would say they are comparably easy. So once you can make a lot of if-else questions, they could be implementable. That's this point here. You have something neural networks thing. So with guys in Linz, I'm at the moment asking how big the neural, so that it can be represented by neural networks is not a question. It's easy to see. Everything is axis parallel. Everything is, it's just classification more or less. So it can be done. The question is, how big do these neural networks need to be to do this stuff here? Okay, yeah, things are also interesting if the measurements are not exact. Exactness is kind of needed here. There are also kind of interesting results if you have noisy measurements, so if you have some random or not random noise. And a particularly interesting question to me, because everything I showed you actually opened a whole door from our side, from the complexity theory side, because we thought linear information is the end of the story. There is nothing interesting from there to non-continuous information. And non-continuous means you can, yeah, that's unrealistic, right? Now we see there seems to be a complexity class in between. Really think of P equals NP stuff. That's type of what we are doing. So there is a complexity class really in between. And this would imply that there are a lot of other classes, complexity classes in this regime. So this is a particularly interesting question. What about other classes of measurements? Assume I'm taking not general linear or general continuous or Lipschitz continuous, I take something more reasonable. For example, assume that the measurements are only norms, or they are only convex functionals, or only homogeneous, or only very smooth functionals, whatever, right? And just as a hookup, is it possible that there is a class of information such that square root of M measurements are needed? Is the setting so rich that you even have a kind of continuous way from going to 0 over log M to M measurements, kind of by restricting the class of information you have? And one remark here, convex is especially interesting because convex functionals can be very nicely approximated on a computer. So for convex programs, there are easy ways to find it. So even if it's a complicated functional, if it's a convex one, there is some chance that you can do it on a computer. That's all I want to say. Thank you very much. Yes, and that's a very interesting question because sparsity actually means that you already know that you are not in several of these colors. So I think you can really replace the M by the sparsity level. After I should need to write it down a little bit, but I'm quite sure that at least for the error 1/2, it's enough to that then you can do sparsity here. No, sure, but this is here. Think of replace this guy by the Kolmogorov numbers, for example, right? And the Kolmogorov numbers have nothing to do with algorithms. They are just a theoretical concept of approximation on a subspace, right? So and so compressed sensing is part of it. We also get an exponential speed up over sparsity then. So if you know sparsity S, you probably only need log S measurements at the end. That would be my guess, but I should need to make the calculations. By the way, the paper is only 10 pages or so. The important part is only 5 pages. Please have a look. I'm proud of it. Again, sorry. Yeah? 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 No, you're right. But and that's the very essence where we were talking about for a while. Thank you. Excellent. So I did not brief him, although we are working together. That is an excellent question. So the point is, assume, and that's what you would like to do. You make a net, a very close net, and just use one information, tell me where you are. Tell me the closest point. Yeah, and this is the way to prove that for non-continuous measurements, you only need one measurement, actually. So more or less, you take a space-filling curve inside of your set, and you just, the one information is, please give me the closest position on this curve, and you're done, right? So that's kind of boring. And so you could do the same here. The problem is, this measurement is not continuous. Because if you want to give me the position, what are you doing here? But that's the point. If you now jiggle around with X a little bit, then you either choose this one or you choose this one, which makes this measurement not continuous. And for us, it was the precise question. So for non-continuous measurements, things are easy, already known. But for continuous measurements, not. And to be honest, we thought that for continuous measurements, it's either this or the same as for linear measurements. We were completely sure that there is a hard line between things are trivial and you need m measurements for m unrelated numbers, because we somehow thought that's related to dimension of the space or whatever. We were somehow surprised that you only need log m here, right? So let me sorry for this, but I need to make one comment. Even if the measurement and the reconstruction is terribly expensive, the guys from the Symbolic Computing Institute in Linz tell me there is still hope that this can be applied to situations where your only goal is compression. So if your goal is you have a big data set and you just want to bring it down to a salt mine for the next 1,000 years in case of atomic war or whatever, then there might be a reason to take this big data set, make our complicated stuff, make it brutally small. Even if the reconstruction takes forever, it might be still worth because we don't have so much space on our planet, right? So to build computers. So they are quite hooked and want to study if this is indeed doable or not as a maybe not fast, but effective compression method.
And we continue after changing the slide.
Where's the button?
Okay, so we continue but from the other institute of mathematics. Ahmed
Oh, thank you, Max. And I would like to thank the organizer for allowing me to give a talk here and also bridging the gap between harmonic analysis and machine learning in some sense. But okay, the talk will be about three different or a mix between three different, let's say, field or or topics. It's about approximation theory in neural network, something from machine learning, and Fourier-Lebesgue space, which is something from harmonic analysis, which I think most of you are aware about this, and I think Harmonder also has this in his second book, as far as I know. And also Joachim somehow has something with this Fourier-Lebesgue space. I would like to say before we start that I can count myself as one from this community because I did my PhD in Turin, under supervision of Sandro Curiasco in this kind of harmonic analysis field, with a lot of collaboration with Joachim, who is here. So let's first draw a picture. Sorry, Marcus, if you would like to turn on the light for some people. But yeah, it's about approximation here. If you have a very big set, and this is y to the x, so kind of the set of functions that are from x to y, and this is really big, what you want is to select a hypothesis space, and this is somehow subspace here, and you call it H. So the hypothesis space maybe is the set of polynomials, set of wavelets, or neural network, why not? And kind of you would like to see what is the approximation rate or the approximation error between your hypothesis class or your selection or your collection of, let's say, atom to the worst element in your original space. And let's assume that this is your function that you would like to approximate. Then maybe this is the approximation error. So this is maybe the best candidate in the hypothesis class that can approximate your function. And this here is the approximation error. Then there is also another error here. Let's say this is f hat and then f hat s. And this somehow an error that comes from samples, and that what Mario is, I think, doing is kind of information-based complexity. So the complexity of studying these kind of samples and so on. And there are other errors about optimization and so on. Right, so that's about approximation here, the approximation error that I'm looking for. So I would like to say also that most of the paper are a joint collaboration with Thomas Dittrich from Linz. And the outline is really basic, so background, some information about neural network and so on, and then the main stuff that I will talk about is about time, space, neural network. And what is that? It's basically, we would like to approximate a solution to some PDEs. That's why we need some time and space. And then if time allows, I will just give some hints about the proof and one example. Right, let's start with the background. So the first, let's say, as far as I know, the first paper was by McCulloch and Pitts in 1943 about neural network, and that was about modeling neurons from biological sense to mathematical sense, and they parameterized it as somehow a parameterized function that has some weights and biases, which are some, you can say, parameters, coefficients, whatever, and it can be written as a composition between nonlinear function with an affine function. The easiest example of that is this shallow neural network. So you have only one composition, you don't have many other layers, that's just one layer. So you just fix the number of neurons that you have, and then you just fix the same activation most of the case, and then you compose this activation with, again, a affine function and multiply with an outer weight and just add the final bias. Just to give an example about activation function, the first was a heaviside function used by Barin and Pitts, Barin McCulloch and Walter Pitts themselves. And it was about if somehow a neuron in biological sense receives some information, and this information has some value and reach somehow threshold, it will fire, and fire means give 1. And if it's not, so it gives some 0. So there will be no signal passing through this neuron. I mean, in biological sense at that time. And then people wanted to study the mathematical stuff, and then they need some regularity. That's why heaviside, it's good function, but sigmoidal is, in some situations, better. In approximation term, they have very close in similarity, but yeah, people try to do things with sigmoidal. Then there are a famous activation function that it is useful up to now in practice, which is called ReLU, rectified linear unit. Mathematically speaking, just maximum function between 0 and x. Not that complicated, but it has a huge implication in practice, and it can be shown that it's first treated, as far as I know, by Nair and Hinton. And this publication in 2010 has more than 27,000 citations, by the way. Then that was a very simple activation, just this function here. So we have 0, and then you have a linear function. Then it has some problems. Then people come to fix this problem, which is called dead neuron, and just a small modification. So you just consider this function, which is called liquid ReLU, and this from 2013. It has more than 10,000 citations. So I'm not promoting any activation function analysis here, but just to say that a small thing in this theory can lead to a huge application in practice. Right. So what is the importance of that from approximation point of view? So 35 years ago, by Sabinko, Horning, and many others, they showed that somehow the neural networks can approximate any continuous function founded on compact domain, actually. And this is called the universal approximation theorem. They have very fancy name, but in the end, from mathematical point of view, it's density argument. You show that this class of function dense in this C omega space, right? Is our shallow neural network is universal? The answer is yes, it is. If and only if the activation itself is continuous but not polynomial. That's one thing. If you have CK here, you need to have rho is a k time differentiable and so on. Right. So let's connect this to the hypothesis space here. And it's well known, I mean, back to Schmidt, I mean, in view of Devore paper, he mentioned that Schmidt was the first one who studied dictionaries, approximation with dictionary. I mean, and what is that? If you have a Banach space, let's say this is your Banach space, and you would like to somehow approximate with a subsection of this Banach space, what you do is you select a nonlinear dictionary that contains some atoms from this dictionary. And atoms mean just collection of functions. And here it's nonlinear because Hj may depend upon the function itself, f. And you would like to, the aim is to approximate the function f from this Banach space using element from this dictionary. Right. And yeah, just a little bit an information about the atom. I thought that it's smaller than the neuron, but it's not. Actually, the atom is smaller than, yeah. I thought that the neurons is smaller than the atom, but it turns out no, it's actually, the atom is even smaller. Anyway, how can this be useful? Actually, they are really efficient in approximation of variation space of the dictionary itself. And what is the variation space? It is, okay, here it's the infimum of all the radius or multiple of the unit ball that make the function back to that. So if you have some unit ball here, your function here, you are looking to increase this unit ball in order to reach this function again, and the smallest r here is the norm. So what is this unit ball? It's basically the closure of the symmetric convex hull, and it's found this way. First studied by Kurkova and many others in connection to neural networks. A very easy example is when your Banach space is the set of LP sequences, and the dictionary is the standard basis. Then the unit ball is this thing, and the norm here is just the L1 norm of the set of sequence of this sequence. All right. Now, what is basically the motivation that somehow lead us to study a problem in connection to Fourier-Lebesgue spaces? First, we thought about the complexity, which is really important to know how many neurons you want, or how many neurons are efficient in your approximation. Because, I mean, you have somehow limited memory and computational resources, and that's why you need to characterize the approximation error here, and not even giving an epsilon. There exists an epsilon, this is an existence theorem, but you need the characterization of this epsilon. Secondly, actually most of the work that at least me and my colleague were at, they deal with single block of variables. So it treat time and space as a one block. So just time is an additional dimension to the space. And for that, this will somehow make some limitation on your analysis here. And you need to somehow strict your norm, your error norm to the least regularity. And you need to use a similar integrability for both variables. Right, so from the space or functional space setting, we need space-time Fourier transform, which are used in dispersive PDE. But to mention, actually, our paper treats much more general, much more general Fourier transform, the one that Elena mentioned, for instance, the partial Fourier transform with respect to the first block of variable, then the partial Fourier transform with respect to the second block of variable, and we see time as a block of variable itself. So, and then we needed mixed Lebesgue space to treat time and space in different integrability. Also, we define what is weighted Fourier Lebesgue space here, just the Fourier transform of the function, multiplying by the weight and then measuring it in the mixed Lebesgue space, mixed Lebesgue norm. And this is a well-known mixed Sobolev space. Right. Those are some ingredients from function spaces, and then from neural network part, we need a dictionary first to treat time and space differently. And for that, we need the affine function to not be the usual affine one, but it has two blocks. So the first treat the time, and the second treat the space. And the activation is not from R to R as usual, and also in practice, that's what you find. But in our case, we use activation from R2 to R. This whole theory can be extended to any n here and multi other blocks with different dimensions. And for that, you define your approximation space in this way. Right. This took up to give the following theorem, and then what is this? Actually, if you have a function in the Fourier Lebesgue space, then you can find somehow constant, somehow approximating your function from this Fourier Lebesgue space with a neural network from sigma n up to the following accuracy. Now, the first question, maybe one can ask, is this rate is optimal? No, it's far from being optimal because there is no information from the regularity of the function on the rate. That's one of the things. The other thing, well, what is the, let's say, what makes this rate important? Actually, there is no curse of dimensionality here. That's one of the good stories. Another maybe comment is about the weight itself. Is it the best weight? Well, it's good, because if you find, for instance, if you have Q1 equal Q2, then here you have only one left and no dimension dependence from the weight itself. Can we do better? For sure, yes, and we are working on that. And want also to say that the existing theory treat only Q equal to 1. So just imagine that you have only one block of variables, so try to forget about time everywhere. So you have this block. So most of the people are treating one block of variable, starting from Baron 1993 up to many other. And usually they select Q2 to be equal to 1, and this is Fourier Lebesgue space, so Q equal 1. And yeah, what we did, actually, somehow we allow this Q to be from 1 to 2. That's what we achieved. And here we allow many P's. So in theory, what you find, either you find a Hilbert space, or you find L infinity, or something like this, like L2, L infinity, and some HL. That's what I'm aware about. But in our case, we increase this P to be from 2 to infinity. So it's more general stuff. Those are some technical, yes, this one is about the regularity. This is mixed Sobolev space. If you want to see, just forget about the down here stuff. So you have WNP, the usual Sobolev space. These ones here. those are the domains. The domain, this is the time domain, this is the space domain. If you have them small enough, then they are really good. If they are bigger, then they may show some dimension dependence here. This C.
Your N1 and N2
Right, the regularity of the norm.
yes. Because they don't appear.
Yeah,
So
we
you
did
can
not
think on
study
that.
optimality of the rate here, but I'm pretty sure that one can do better stuff, and one can refer to Siegel paper where he achieved some rate that depends also on the regularity, and the dimension also, but in higher dimension, that won't be helped too much because you get like -1/2 minus, let's pick n, minus n2 over d2, for instance, and if d goes to infinity, then there's no big implication from that. Yeah. I hope that I have time to discuss the proof, and basically 5 steps to give the proof, but first or main step is we would like to show that all the settings that we have satisfy the assumptions of Mori approximation. Basically, we want to show that that we have a two Banach space or type 2 Banach space. This error norm here should be type 2 Banach space, and right. So also we need to show that the function is in the variation space. We need to show that this constant here, somehow the dictionary is uniformly bounded in your Banach space, and so on and so on. So yeah. So what you do is basically you write the activation function in terms of the Fourier transform. You do a simple change of variable. You pick the phase out, and then you have some characterization of the phase here. This one will be used in definition of the function itself. So the function is really good one. You can define it this complicated way. We have a cosine and not a phase here because the function is a real valid one. After checking, after many steps here, we check that the function f belongs to the variation space. So this is one step. Secondly, we need to give an upper bound of the variation norm, and that means that the function here is uniformly bounded. In this, that the function belongs to this variation space. Yeah, and here we show that the dictionary is bounded. So, sigma tilde here is, or our set of dictionary is the set of sigma tilde. I just recall how the dictionary is defined is this way, right, this way. So we would like to show that this is uniformly bounded in our Banach space. All right, and it is. And then we combine all the previous steps to satisfy Maury sampling argument to get the final result. Right, and an easy example here is the following. So imagine that you have the two-phase heat equation, and then this is the solution here, and you would like to approximate it. Now, if you use the standard or the existing setting, you need to have only one single block of variable that treat time and space in the same activation function. And you imagine that, let's imagine that you use the ReLU to the power 2. But in our setting, we use the product of ReLU and ReQ. So, ReLU to the power 1 and time the ReLU to the power 2. With that, the two block, our construction here achieved the same rate as the single block with half of the number of parameters, almost. So we allow fair comparison here. We give the same number of parameters for both network and train them in 100,000 epochs. 10 times, so you run simulation 10 times, you throw these weights and biases randomly 10 times, and then you see the average here. In both cases, the two blocks somehow beats the one block. And also from the image here, this is the target function, and this is the derivative of the target function. The single block cannot handle the sharp edges, but the two blocks did it. it's pretty close also from the pictures. And also here the same. I mean, the 2 blocks is better than the 1 block in terms of picture and also approximation. I mean, the rate is still not the optimal, just to recall that. Yeah, that's it from my part, and thank you.